You let your mind rest on the quiet idea that reaching the moon is not a mystery but the result of careful work built on centuries of observable science. You begin with simple motion, the way an object responds when a force pushes it. Isaac Newton described this relationship in mathematical form, showing how acceleration depends on mass and force. Every rocket ever built follows these laws without exception. You picture a small demonstration. When gas rushes out of a nozzle in one direction, the rocket is pushed in the opposite direction. It is not magic or guesswork, only the measured behavior of action and reaction, confirmed in laboratories and open fields long before large spacecraft existed. You follow the story as it grows from these early principles. Throughout the 19th and early 20th centuries, scientists such as Konstantin Tsiolkovsky calculated that liquid-fueled rockets could, in theory, reach space. His work relied on equations still used today, including the rocket equation, which relates velocity change to propellant mass and exhaust speed. You imagine him writing numbers in quiet rooms, knowing that the physics was sound even before technology was ready. Years later, Robert Goddard built the first liquid-fueled rockets, proving in measured tests that controlled combustion could lift a craft upward. Every flight produced data: thrust curves, fuel flow rates, and altitude readings. Nothing was assumed. Everything was recorded. As nations advanced their understanding of aerodynamics and propulsion, the foundations of spaceflight solidified. Engineers learned how to shape fuel tanks, stabilize fins, and build guidance systems that kept rockets pointed correctly. The development of gyroscopes allowed machines to sense their orientation. Radio tracking allowed ground teams to follow flight paths with accuracy. These technologies were tested repeatedly on sounding rockets and early satellites. With each flight, engineers collected telemetry, precise numerical streams showing pressure, temperature, acceleration, and structural loads. These measurements guided improvements, removing guesswork and replacing it with confirmed performance. When the idea of sending humans to the moon emerged, the science behind it was already well established. The goal was not to discover new physics but to apply known physical principles with extraordinary precision. Engineers needed a rocket strong enough to push heavy modules into space, a spacecraft safe enough to support life, and navigation systems stable enough to place the crew on the correct path. Every requirement was grounded in physics that had been repeatedly tested. There was no shortcut, only detailed engineering combined with reliable formulas that had been proven in both experiments and flight. You picture the Saturn V as it slowly comes into view, not as an icon but as a precisely measured machine. The vehicle stood more than 110 meters tall and consisted of millions of individual components, each documented and tested. Its power came from chemical energy stored in liquid oxygen and kerosene for the first stage, and liquid hydrogen for the upper stages. Combustion tests measured the exact exhaust speed of the gases, allowing engineers to calculate the thrust of each engine. The numbers were confirmed on static test stands long before the rocket ever flew. The first stage, known as the SIC, used 5 F1 engines, each producing more thrust than any engine before or since. Engineers studied how fuel flowed through pumps, how pressure built inside the combustion chamber, and how nozzles handled the intense heat. High-speed cameras recorded flame behavior. Sensors captured vibrations and bending forces. If any reading exceeded safe limits, design teams adjusted structures or materials. By the time the Saturn V flew, its performance envelope was not theoretical. It was measured with precision. Above it, the second stage used 5 J2 engines fueled by liquid hydrogen, producing a clean and efficient burn. The third stage used a single J2 engine capable of restarting in orbit, a requirement for the long injection burn that would send astronauts toward the moon. These stages were not isolated pieces. They were integrated with avionics, fuel lines, control systems, and sensors, all communicating with ground stations. Each flight before Apollo 11 served as another data point, confirming that the rocket behaved as predicted. But propulsion was only one part of the path. You learn how engineers built a spacecraft capable of protecting humans from the vacuum of space. The command module's pressure vessel was constructed from tested aluminum alloys. Its life support systems maintained oxygen levels, humidity, temperature, and carbon dioxide removal based on documented physiological needs. Water and oxygen reserves were calculated using medical studies. Every valve, filter, and electrical pathway was tested. The lunar module, shaped like a lander rather than an aircraft, was designed for a vacuum environment and low gravity. Its thin walls were strong enough because there was no external air pressure to resist. Engineers studied its structure under simulated lunar loading conditions, verifying that it could stand on the moon's surface without issue. Guidance and navigation relied on real-time measurements. Inertial measurement units tracked movement with spinning gyroscopes and accelerometers. These devices detected rotation and acceleration, allowing computers to calculate position without relying on external references. Radio communication provided an independent check, with signals timed precisely so ground stations could determine spacecraft distance through ranging techniques. Doppler tracking added another layer, detecting tiny frequency shifts caused by motion. All these methods were grounded in physics and engineering that had been validated over decades. Astronaut training formed another measured part of the process. Simulators reproduced spacecraft controls using real electrical systems. Neutral buoyancy tanks allowed crews to practice movements in conditions similar to microgravity. Meteorological studies helped determine safe launch windows. Geologists trained astronauts to recognize different types of lunar rocks, preparing them to gather scientifically valuable samples. Every part of the mission was rehearsed in careful, documented steps. You notice how none of this relied on leaps of faith. It relied on the accumulation of evidence. Each subsystem, material, and component was tested at the limits of what science and engineering could control. When the Saturn V finally lifted from the launch pad, the plume of fire beneath it was not a dramatic gesture, but the predictable result of chemical energy turning into momentum exactly as physics described. The rocket rose because thrust exceeded its weight. It followed a programmed trajectory that balanced gravity, drag, and fuel efficiency. Telemetry streamed back to Earth, confirming each parameter as the vehicle climbed. You rest on the thought that reaching the moon was never about pushing against the unknown but applying known principles with unmatched coordination. The work required time, discipline, and thousands of small verifications. And as the giant rocket left Earth behind, all the measurements, calculations, and engineering choices aligned in a moment that showed how far careful science could carry the human body and mind. You stay with the quiet recognition that this journey began long before the spacecraft reached space, starting with simple laws of motion and growing into machines capable of crossing the distance between worlds. And as you settle into that understanding, you feel a gentle curiosity forming about the environment waiting beyond Earth, shaped by observations that reveal what the moon truly is and what its surface holds. You let your thoughts settle on the moon not as a distant symbol but as a measurable, physical world. When you look at it through a telescope, you see patterns of light and dark created by real geological formations. The brighter regions are highlands made of ancient, heavily cratered rock. The darker areas are basaltic plains formed by past volcanic activity. These features are not guessed at. They are mapped in detail through high-resolution imaging, both from Earth and from dozens of orbiting spacecraft that have measured the surface with precision. You notice how early astronomers described the moon's landscape long before spacecraft reached it. They used careful observations to count craters, estimate mountain heights from shadow lengths, and identify smooth plains that hinted at volcanic flows. Their predictions were confirmed when orbiters such as Lunar Orbiter, Clementine, and later the Lunar Reconnaissance Orbiter sent back detailed photographs and laser altimeter data. These measurements revealed elevation maps accurate down to meters, showing ridges, impact basins, and long, winding channels formed by ancient lava. You follow the story deeper as scientific instruments reveal the moon's interior. Seismometers placed during Apollo missions recorded vibrations caused by meteor impacts and thermal expansion. These signals traveled through layers of rock, allowing scientists to infer the moon's internal structure. Data showed a crust about 30 to 50 kilometers thick, a mantle extending hundreds of kilometers below it, and a small, partly molten core. The readings required no speculation. They reflected real seismic waves, measured over years and analyzed by comparing them to known patterns of wave motion through solid and molten materials. You begin to understand the moon's formation through evidence gathered from multiple sources. The giant impact hypothesis proposes that a collision between the early Earth and a Mars-sized body produced debris that eventually formed the Moon. This idea is supported by several lines of measurable data. Lunar samples brought back by Apollo missions show oxygen isotope ratios nearly identical to Earth's mantle, suggesting a shared origin. At the same time, the Moon contains far less iron than Earth, consistent with debris originating from the outer layers of a collision rather than from deep metallic cores. Computer simulations based on physics of high-energy impacts reproduce these patterns, strengthening the evidence. You picture the lunar soil or regolith, not as dust floating loosely but as a fine, powdery layer formed by billions of years of micrometeorite impacts. Every tiny collision shattered rock into grains, melted surfaces into glassy beads, and mixed material across the landscape. Samples returned from the Moon show sharp-edged particles because there is no wind or water to smooth them. Their mineral content includes plagioclase, pyroxene, olivine, and fragments of glass formed during impacts. These compositions match what orbiting spectrometers observe when they measure the wavelengths of light reflected from the surface. You also learn how light behaves differently on the Moon. With no atmosphere, sunlight is unfiltered and shadows are extremely sharp. Temperature swings are extreme because there is no air to distribute heat. Measurements show that sunlit areas can reach around 120 degrees Celsius, while shaded regions drop to about -170 degrees Celsius. Instruments have recorded these values repeatedly, confirming them over decades. When astronauts prepared to land, they trained using these numbers to understand the thermal load their suits and equipment would need to withstand. You pause on the Moon's gravity about 1/6 of Earth's, measured by timing how objects fall and by tracking spacecraft trajectories. This reduced gravity affects how dust moves, how rocks rest on slopes, and how easily astronauts could lift equipment. Lunar gravity data also help scientists map the density of material below the surface. By observing small shifts in spacecraft speed as they pass over regions of greater or lesser mass, missions such as GRAIL produce gravity maps that reveal buried structures, including ancient impact basins and solidified magma chambers. You picture the Moon's quietness. With no atmosphere, sound cannot travel. The environment is still, but sensors detect constant tiny impacts from dust-sized meteoroids. Instruments have recorded these strikes, helping scientists estimate how the surface evolves over time. Even now, new craters form regularly, confirmed by before and after images taken by orbiters. These observations show that the Moon is not static but slowly changing through natural, measurable processes. You turn your attention to the absence of weathering. Without wind, water, or biological activity, footprints remain intact unless disturbed by impacts. The Apollo landing sites, imaged by modern orbiters, still show paths traced by astronauts and tracks from equipment. These preserved markings provide a natural laboratory for studying how the surface responds to sunlight, micrometeorites, and electrostatic charging over long periods. Electrostatic effects, measured by instruments and inferred from dust movement, come from the interaction of solar ultraviolet radiation and solar wind particles with the surface, causing tiny grains to become charged. You consider the Moon's orbit, shape, and rotation. Its synchronous rotation means one hemisphere always faces Earth, a phenomenon explained by tidal locking. Measurements show that the Moon once rotated faster, but gravitational interactions gradually slowed its spin until the same side remained turned toward Earth. Laser ranging experiments using mirrors left by astronauts measure the Moon's distance to millimeter precision. These data confirm that the Moon drifts away from Earth by about 3.8 centimeters per year, a rate expected from well-established tidal physics. You also learn how much planning went into understanding the environment astronauts would encounter. Radiation levels were measured by orbiters and calculated based on solar activity and cosmic rays. Surface hardness was estimated through radar reflections and later confirmed by lander footpads that pressed into the soil. The stability of slopes was studied from imagery and from the distribution of boulders. Engineers used these findings to design landing systems capable of handling uneven terrain. Life support systems were built to manage the Moon's extreme temperatures, vacuum, and abrasive dust. You imagine how this knowledge shaped human expectations before the first landing. Astronauts knew the ground would feel firm beneath them, based on probe readings. They knew the sky would appear black even in daylight because no atmosphere scatters sunlight. They knew that each step would send dust arcing farther than on Earth due to lower gravity. These predictions were not hopes but calculations supported by measurements from multiple missions. You rest in the understanding that every detail about the moon, its surface, its interior, its formation, and its environment, comes from instruments, observations, and samples that scientists still study today. And as you let these facts settle, you feel a quiet curiosity forming about how the human body and mind adapted to working in a place shaped so differently from Earth. You begin with the quiet observation that leaving Earth is a matter of measurable physics rather than imagination. Gravity is a force pulling everything toward the planet's center. Every object experiences this force in proportion to its mass, just as Newton described. To move away from Earth, a spacecraft must generate enough upward acceleration to overcome gravity. This requirement is not an estimate. It is calculated using mass, force, and the acceleration necessary to achieve orbit or escape entirely. These calculations form the foundation of every rocket launch ever conducted. Thrust is the primary way rockets counteract gravity. It arises from the reaction of propellant expelled at high speed through a nozzle. You visualize the principle in simple terms. For every kilogram of fuel pushed downward, an equal and opposite force pushes the rocket upward. Engineers measure exhaust velocity and propellant flow to calculate how much thrust is available at any moment. These measurements are critical as insufficient thrust will prevent ascent, while excess thrust without proper guidance could destabilize the vehicle. Every engine is tested repeatedly on the ground to verify that the numbers match theoretical predictions. Escape velocity is another crucial concept. It is the speed an object must reach to leave Earth's gravitational influence without further propulsion. At Earth's surface, this velocity is roughly 11.2 kilometers per second. Rockets achieve this not in a single burst but through carefully staged acceleration. Each stage contains its own engines and propellant, designed to burn efficiently and then detach once depleted. Measurements of thrust, burn duration, and mass allow engineers to predict the final speed with high accuracy. Staging is not a suggestion, it is a requirement dictated by the physics of lifting enormous masses against gravity. Orbital mechanics govern how spacecraft move once they leave the lower atmosphere. A spacecraft in orbit follows a path determined by the gravitational pull of Earth and its own velocity. By adjusting speed and direction, engineers can insert the craft into a stable orbit or direct it toward the moon. Every trajectory calculation relies on tested formulas derived from Newtonian mechanics, augmented by observations of how objects move in space. These calculations are confirmed by tracking satellites and prior missions, providing a real, repeatable understanding of motion in the vacuum beyond Earth. Rockets must also operate in a vacuum, which changes how engines function. Combustion in space relies on carrying both fuel and oxidizer, as there is no atmospheric oxygen. Engineers carefully measure combustion chamber pressure and nozzle expansion to optimize thrust under these conditions. Laboratory tests replicate vacuum conditions using large chambers, providing real data on how propellant burns and how exhaust interacts with the surrounding environment. Nothing is assumed. Every value is observed and verified. Guidance systems are another essential part of leaving Earth. Inertial measurement units, using gyroscopes and accelerometers, track the spacecraft's position and orientation continuously. The readings are processed by onboard computers to adjust engine gimbals or small thrusters, keeping the craft on its planned trajectory. These systems are tested rigorously against ground simulations, and telemetry sent back to Earth confirms performance in real time. Ground control monitors speed, altitude, and orientation, cross-checking all measurements to ensure accuracy. Every adjustment is based on measurable, documented data rather than estimation. Telemetry itself is an extension of physics applied to communication. Radio waves transmit readings from the spacecraft to receivers on Earth. Engineers measure frequency shifts, signal strength, and time delays to determine position and velocity precisely. The Doppler effect is accounted for, allowing controllers to detect even small deviations from the planned trajectory. Telemetry provides a continuous stream of quantitative evidence that the vehicle is performing according to calculations and expectations. The Saturn V demonstrates the practical application of these principles. Its first stage, equipped with 5 F1 engines, produces over 33 million newtons of thrust. Engineers verify the performance of each engine on static test stands, recording exhaust velocity, chamber pressure, and fuel consumption. Data from these tests ensures that the vehicle can lift its enormous mass into the lower atmosphere. The second and third stages are optimized for operation at higher altitudes and near vacuum conditions, with burn durations calculated to achieve the exact speed and direction necessary for lunar transfer. Each stage's separation is timed precisely, confirmed by accelerometer readings and radar tracking. As you consider the flight path, you realize that achieving orbit does not mean leaving Earth entirely. The spacecraft first enters a stable orbit around the planet, matching velocity with the curvature of the surface. From this orbit, a precisely calculated engine burn propels the vehicle toward the Moon. Engineers determine the timing, angle, and thrust of this burn using Newton's laws applied to orbital dynamics. These calculations are verified by simulations and prior mission data, ensuring that the craft's trajectory intersects the Moon's orbit accurately. Fuel management is another layer of precision. Every kilogram of propellant is accounted for, and burn rates are monitored continuously. Sensors measure tank pressure, flow rates, and temperature to confirm that engines operate within expected parameters. These readings allow mission control to calculate remaining delta V, the change in velocity available, ensuring that the spacecraft has sufficient energy to reach the Moon. Fuel staging, monitoring, and verification are entirely based on physics and empirical testing. You also observe the importance of angular momentum. The orientation of the spacecraft affects not only navigation but also the efficiency of engine burns. Reaction control systems make small adjustments using thrusters, guided by accelerometer readings. Every movement is measured, recorded, and cross-verified with gyroscope data, allowing the crew and ground control to maintain precise control. Even the slightest error could accumulate, altering the trajectory significantly. The physics governing these adjustments are well understood and repeatedly confirmed through simulation and flight tests. Temperature and structural forces are measured carefully, as leaving Earth imposes extreme conditions. Dynamic pressure during ascent and aerodynamic forces on the vehicle are monitored through strain gauges and accelerometers. Engineers predict stress points and test them before flight. Thermocouples measure heat generated by engine exhaust and friction with the atmosphere. All of these readings are used to verify that the structure behaves as expected, with no assumptions about unknown factors. The process of leaving Earth is therefore a chain of verifiable, measured events. From engine ignition to staging, orbit insertion, and translunar injection, every step is grounded in physics. Each value is tested on Earth, simulated in vacuum chambers, and confirmed through telemetry in real missions. Nothing occurs by chance, and every calculation can be independently verified using known laws of motion, gravitation, and energy. This is why engineers can predict spacecraft behavior with remarkable precision, long before any human is on board. As you rest on these facts, you appreciate the care required to translate mathematical principles into mechanical reality. You understand that each motion, each adjustment, is a direct application of Newton's laws and orbital mechanics, validated by countless measurements. The flight path is not abstract. It is a continuous, observable process of acceleration, force, and trajectory control. You end with a quiet readiness to follow the Apollo 11 spacecraft into the vacuum of space, where the known physics of radiation, temperature, and microgravity await precise observation, measured and predictable, revealing how humans move, work, and exist in an environment beyond the pull of Earth. You imagine the spacecraft now moving steadily through the quiet expanse above Earth. In the vacuum of space, there is no air to resist motion, and no friction to slow progress. The spacecraft coasts along a trajectory carefully calculated before launch, following the principles of orbital mechanics. Its velocity and position are not estimated. They are continuously measured by onboard instruments and confirmed by ground stations tracking radio signals. These measurements provide real-time data that allow mission control to verify the path and make adjustments if necessary. Mid-course corrections are small but precise. Thrusters fire for brief intervals to adjust speed or direction, ensuring the spacecraft stays on its planned path. Each burn is calculated using Newton's laws, accounting for mass, velocity, and gravitational influences from Earth, the Moon, and, to a minor extent, the Sun. Telemetry confirms that every thrust produces the expected change in velocity. The accuracy of these maneuvers is verified using both onboard instruments and radar tracking from Earth, allowing scientists to predict where the spacecraft will intersect the Moon's orbit to within a few kilometers. The guidance system relies on gyroscopes and accelerometers to detect rotation and acceleration. These instruments feed data to onboard computers, which calculate orientation and required adjustments. Even in the absence of external reference points, the inertial guidance system allows the spacecraft to maintain its correct trajectory. Engineers confirmed the reliability of these systems through extensive simulations and previous unmanned missions, providing measurable confidence that the spacecraft could navigate the long journey with minimal deviation. Radiation in space is another environment to consider. Outside Earth's protective magnetic field, cosmic rays and solar particles pose a risk. Instruments on board measure radiation levels continuously. The spacecraft itself provides some shielding, and crew exposure is limited by timing and monitoring. These measures are based on documented studies of particle interactions with spacecraft materials, ensuring that the astronauts remain within safe exposure limits. Solar activity is predicted using satellite observations, allowing mission planners to anticipate periods of higher radiation and make necessary adjustments to operations. Thermal control is essential in a place without atmosphere. Sunlight warms one side of the spacecraft intensely, while the opposite side can cool to extreme lows. Sensors measure surface and interior temperatures, and systems circulate coolant to maintain acceptable conditions. Multilayer insulation, reflective coatings, and heat exchangers all function according to physics principles that have been tested on Earth and in orbit. Telemetry confirms that these systems keep instruments and crew within operational limits, providing measurable, predictable outcomes rather than relying on estimation. You notice the careful management of the spacecraft's internal atmosphere. Oxygen levels, carbon dioxide removal, and humidity are continuously monitored. Air circulation ensures even distribution of temperature and gas composition. Sensors alert astronauts and ground control if conditions drift from acceptable ranges. Every adjustment is guided by known chemical and physical processes, verified through long-term observations and experiment. Drinking water and food are prepared to function reliably in microgravity, with packaging and delivery systems tested extensively to avoid contamination or spoilage. Microgravity alters nearly every aspect of life aboard the spacecraft. When you move, your momentum is preserved, and small forces can send objects drifting. Engineers and astronauts learn to adapt through both simulation and prior missions. Restraints, footholds, and handrails are carefully positioned based on measured patterns of motion. Eating, drinking, and waste management are all adjusted to account for these conditions. Every procedure is based on tested behavior observed in orbital flights, providing predictable results that maintain safety and efficiency. Communication with Earth is continuous. Radio signals relay telemetry, voice, and scientific data. Engineers calculate time delays and signal strength, ensuring that commands and responses remain accurate. Doppler shifts from the spacecraft's motion are accounted for in calculations, allowing precise determination of velocity and distance. Every transmitted signal confirms the spacecraft's trajectory and environmental conditions, forming a chain of measurable observations that provide certainty throughout the journey. You observe how astronauts performed experiments and collected data while traveling. Cameras documented Earth and space phenomena with calibrated instruments. Radiation detectors, magnetometers, and particle counters provided continuous streams of quantitative measurements. Every reading was logged and transmitted, verified against prior data, and compared to expected values. The environment itself becomes an instrument, with each measurement forming part of a larger understanding of space between Earth and the Moon. Navigation relies on both predicted and observed positions. Star sightings, combined with inertial measurements, allow crew and mission control to cross-check calculations. Every position fix is measured, not assumed. The spacecraft's trajectory is confirmed repeatedly, allowing small corrections to be planned and executed precisely. These procedures ensure that the vehicle remains on course for lunar insertion, following paths determined entirely by physics and verified by observation. Supplies are rationed according to calculated consumption. Food, water, and oxygen are stored in measured quantities, allowing for small deviations but designed to last for the planned duration of travel. Measurements of mass, volume, and chemical composition confirm that life support systems provide what is needed. Any discrepancy would be immediately detected through sensors and telemetry. This careful management transforms abstract planning into real, measurable results for human survival. You notice the discipline in timekeeping and coordination. Clocks on board are synchronized with Earth-based atomic standards. Every activity, from engine burns to experiment intervals, is scheduled and verified. Even small timing errors can affect trajectory or radiation exposure. Precision timing is not a convenience but a necessity, grounded in physics and confirmed by observation, ensuring that each decision is informed by real data. You reflect on the stability of the spacecraft systems. Vibrations, pressure changes, and temperature fluctuations are monitored continuously. Any deviation beyond acceptable tolerances triggers alarms and responses based on measured thresholds. These responses are predetermined, calculated from engineering tests, and verified in practice during previous flights. This system of continuous monitoring allows astronauts to move, eat, and work confidently, relying entirely on tested knowledge rather than assumption. The coasting period between Earth and the Moon is long, quiet, and controlled. You imagine drifting alongside the spacecraft as it glides through empty space, every movement accounted for by laws of motion and measured by instruments. The entire environment is predictable, governed by established principles of physics that have been observed, recorded, and verified. Each day brings new readings from instruments confirming that the spacecraft remains on course, that temperatures and pressures are within expected limits, and that radiation exposure is safe. Every action, from small thruster firings to life support monitoring, is a result of accumulated evidence. Engineers and astronauts rely on measurable, repeatable observations rather than guesswork. Calculations, simulations, and prior flights provide certainty about the spacecraft's behavior. Telemetry, combined with onboard sensors, forms a continuous chain of verification, ensuring that each adjustment and response is documented and understood. You rest with the realization that space is not an unpredictable void, but a well-understood environment where motion, energy, and matter behave according to established physical laws. Observations, measurements, and calculated interventions guide the journey with remarkable precision. As you consider this, you feel a quiet awareness of the Moon growing closer, and the exact calculations, tracking, and controlled maneuvers that will guide the spacecraft into orbit around another world. You begin by imagining the spacecraft approaching the Moon, its trajectory guided by precise calculations from Earth. The Moon's gravity begins to influence the spacecraft subtly, altering velocity and direction. These effects are not hypothetical. They are measured and predictable. Engineers calculate how the spacecraft must adjust speed and orientation to enter a stable orbit, using the Moon's mass, the craft's velocity, and Newton's laws of motion. The numbers are exact, derived from years of observation and repeated verification with previous missions and unmanned orbiters. As the spacecraft nears the Moon, mission control prepares for the engine burn required for orbit insertion. The main engine must fire for a specific duration at a precise moment, altering velocity just enough to capture the spacecraft into lunar orbit. Telemetry data confirm the timing, throttle settings, and remaining fuel. Every parameter is monitored in real time, providing immediate confirmation that the maneuver behaves according to calculations. These readings rely on verified instruments and do not involve guesswork. The concept of orbital mechanics is central to this maneuver. To maintain a circular or elliptical orbit, the spacecraft's velocity must match the curvature of its path around the Moon. Too fast, and it would escape lunar gravity. Too slow, and it could descend prematurely. Engineers calculate the required velocity based on mass, altitude, and gravitational acceleration, with numbers confirmed through both simulations and prior lunar missions. The accuracy of these calculations is measured in meters per second, allowing spacecraft to enter orbit predictably. Fuel margins are critical. Every kilogram of propellant is accounted for to ensure that orbital insertion and subsequent maneuvers can be performed safely. Sensors measure tank pressure, flow rates, and temperature, confirming that engines deliver expected thrust. Data from the burn is compared to pre-flight predictions, and any deviations are analyzed to determine if additional corrections are needed. This method ensures that there is sufficient energy to remain in orbit or to adjust for minor errors without risk. Gravitational interactions between Earth, Moon, and spacecraft are subtle but measurable. Engineers calculate perturbations caused by the Earth's gravity, which continues to influence the trajectory even at this distance. Lunar mass concentrations, or mascons, create small variations in the gravitational field that can slightly accelerate or decelerate the spacecraft. These variations are not theoretical, they are mapped using orbiters and previous mission data. Calculations for orbit insertion take these into account, ensuring that the spacecraft enters a stable and predictable path. Telemetry plays a central role in monitoring the orbit insertion. Signals transmitted to Earth carry measurements of acceleration, velocity, orientation, and engine performance. Doppler shifts provide precise velocity data, and radar tracking verifies position to within a few meters. Engineers compare real-time measurements to calculated predictions, confirming that the spacecraft is responding exactly as expected. Each adjustment is based on verified data, not estimation. The burn itself is carefully controlled. Reaction control systems stabilize orientation during the main engine firing, preventing unwanted rotation that could reduce efficiency. Gyroscopes and accelerometers provide continuous feedback to the guidance computer, which adjusts engine gimbals and thrusters. The system has been tested extensively on Earth and in prior missions, confirming that the spacecraft can maintain the necessary alignment. Every movement during the burn is recorded, forming a complete, measured record of the maneuver. Once the burn is complete, the spacecraft's velocity is within the precise range required for lunar orbit. Sensors measure speed and altitude, confirming that the orbit is stable. Mission Control verifies this with radar and Doppler data, confirming position and trajectory. Engineers calculate the orbital period and eccentricity, ensuring that it matches the plan for subsequent maneuvers. These calculations are based entirely on Newtonian physics and verified observational data. You notice that orbital insertion is not a single instant but a series of continuously monitored adjustments. Small thrusters fire to fine-tune position and orientation. Each adjustment is based on measurable deviations detected by gyroscopes, accelerometers, and radar tracking. The spacecraft's path is continually cross-checked against predicted values, and any correction is calculated precisely. These procedures ensure that the orbit remains safe and predictable, providing a foundation for the upcoming descent toward the surface. The Moon's environment itself influences the orbit. There is no atmosphere to slow the spacecraft, so once velocity is adjusted, it remains effectively constant except for gravitational perturbations. Thermal conditions are monitored to ensure that sunlight does not overheat sensitive equipment. Radiation sensors confirm exposure levels remain within safe limits. Each of these measurements informs decisions about maneuvers, equipment operation, and crew safety. The environment is predictable because it is documented and quantified. You also consider the importance of timing. The insertion burn must occur at a specific point along the trajectory to achieve the desired orbit. Calculations account for distance traveled, velocity, and gravitational influence, all verified through simulations and previous measurements. Telemetry confirms the exact position at which the burn begins, ensuring that the resulting orbit is aligned with the planned approach for the lunar module's separation. This precise coordination reflects the application of physics to a moving, real-time system. The spacecraft's instruments continue to provide constant feedback. Accelerometers measure changes in velocity, gyroscopes track rotation, and optical devices verify attitude and orientation. Engineers cross-reference these measurements with predictions, confirming the accuracy of the orbit insertion. Every reading is documented, forming a verifiable record of the spacecraft's behavior. These observations are not abstract. They are measured phenomena that can be reproduced and confirmed independently. You observe how safety margins are incorporated into the calculations. Engineers design maneuvers with slightly more fuel and slightly adjusted timings to account for minor uncertainties. These margins are based on empirical data from previous missions, not assumptions. Every decision is grounded in the principle that measured quantities, verified repeatedly, reduce the risk of error. Even small deviations are corrected with subsequent burns, each guided by real-time telemetry. As you settle into this understanding, you see the elegance of applying known physics to a complex, moving system. The spacecraft moves predictably around the moon, following calculated paths verified through instruments, telemetry, and repeated observations. There is no ambiguity. Every parameter is measured, every adjustment is verified, and every action has a clear, documented purpose. The orbit is stable because all contributing forces, gravity, engine thrust, spacecraft mass, are understood and accounted for. You rest on the awareness that entering lunar orbit is a controlled, measurable achievement, one that relies entirely on known laws of motion, verified instruments, and continuous observation. Each rotation around the moon is predictable, each altitude is confirmed, and each velocity is recorded. And as the spacecraft circles silently, you feel the quiet anticipation of the next phase, when measured maneuvers will guide it closer to the surface of another world, ready for precise, controlled descent. You begin by visualizing the lunar module, Eagle, separated from the command module and descending toward the moon's surface. The spacecraft's velocity and altitude are continuously measured using radar, altimeters, and accelerometers. Every reading is transmitted to mission control, confirming that the descent follows calculated parameters. The engines provide variable thrust, measured and adjusted in real time to control the rate of descent. The guidance system processes this data, issuing commands to the engine gimbal, ensuring the craft remains on its intended trajectory. The physics of landing on the moon are measurable and precise. The lunar surface provides no atmospheric resistance, so the module cannot slow by aerodynamic drag. Deceleration is achieved entirely by thrust directed opposite to motion. Engineers calculate exactly how much force is needed to reduce velocity to a safe touchdown speed, accounting for the spacecraft's mass, fuel consumption, and gravitational acceleration, which is roughly 1/6 of Earth's. Telemetry confirms that each thrust produces the expected change in speed. The descent engine is throttleable, an important feature verified through testing on Earth and in prior missions. Sensors measure chamber pressure, nozzle expansion, and propellant flow. Adjustments are made continuously based on accelerometer readings and altitude measurements. These readings are precise and repeatable, ensuring that the landing sequence is predictable. Mission control monitors these numbers to confirm that the module is within expected limits at every stage. You observe how the landing radar functions. It measures distance to the surface by sending pulses and recording the time until return. The data allows calculation of altitude and vertical speed, providing real-time information for guidance. Doppler measurements track horizontal motion and confirm alignment with the planned landing site. These readings are continuously compared to predicted values, allowing the system to correct deviations automatically or with crew input. Every measurement is grounded in well-understood physics. Lunar dust behaves differently than soil on Earth. When the engine plume interacts with the surface, particles are displaced, but there is no air to scatter them widely. High-speed cameras on previous test landings and lunar observations confirm that dust is ejected in arcs determined solely by thrust and gravity. Observations from orbiting spacecraft and returned samples validate these patterns. The dust's behavior is a predictable consequence of vacuum conditions and particle physics, measured repeatedly in simulations and laboratory experiments. The astronauts' movements inside the module are adapted to low gravity and acceleration. Small control inputs result in smooth, measurable changes in orientation. Each lever, switch, and hand movement has predictable effects on the spacecraft. Mission transcripts confirm that astronauts adjusted thrust carefully, guided by real-time numerical readings rather than intuition. These adjustments are part of a continuous feedback loop that ensures the lander descends safely. Fuel management is a critical component of landing. Sensors continuously monitor remaining propellant, flow rate, and pressure. Engineers calculate the burn duration required for final descent and reserve margins to handle minor corrections. Every maneuver is backed by documented calculations and verified by telemetry. The module's mass decreases as fuel is consumed, and the guidance system accounts for this change in real time, maintaining precision in both vertical and horizontal motion. Landing site selection is informed by detailed orbital photography and prior measurements of surface slopes, boulder distribution, and crater density. The goal is to touch down on stable ground with minimal risk. Orbital images are analyzed quantitatively, measuring elevations, slopes, and distances. These data are used to plan exact descent coordinates and verify that the module will reach the intended location. Precision is measurable, and no assumptions are required beyond documented observations. The module's attitude is continuously monitored. Gyroscopes measure rotation, and onboard computers compare readings with predicted values. Thrusters make minor adjustments to maintain level orientation and alignment with the landing point. Telemetry confirms that each adjustment produces the expected effect on orientation and velocity. These readings allow the crew to trust that the module is descending according to plan, and ground control confirms the data through independent radar tracking. You notice that the descent is incremental. Velocity decreases gradually, altitude is measured continuously, and engine output is adjusted to match predictions. This gradual process ensures stability and allows for small corrections. Each measurement of speed, acceleration, or altitude is cross-checked by multiple instruments, providing redundant confirmation of the lander's behavior. The physics governing motion, thrust, and gravity are applied consistently, leaving no room for guesswork. As the module nears the surface, the rate of descent slows to a few meters per second. Radar confirms altitude within meters, and accelerometers provide verification of vertical acceleration. The astronauts make minor manual adjustments as needed, guided by precise numerical displays. Every control input is predictable, and the resulting motion matches expectations. Even the dust displaced by the engine plume follows trajectories that correspond exactly to calculations based on gravity and particle dynamics. Touchdown occurs when landing pads make contact with the lunar regolith. Load sensors measure the force transmitted through the pads, confirming that the module has settled on stable ground. Engine thrust is reduced to zero, verified by pressure readings and telemetry. The spacecraft is stationary, and the surface supports the mass as predicted. Instruments confirm that the landing was within all planned parameters for velocity, orientation, and location. You notice the absence of atmosphere in the resulting observations. Shadows are sharp, dust remains in place except where disturbed by the engine or boots, and light behaves according to measured reflectivity of the lunar surface. Cameras record these conditions quantitatively, confirming the physical behavior of light, dust, and terrain. Each effect aligns with verified observations and laboratory measurements. Environmental measurements are ongoing even after landing. Radiation levels are recorded continuously, and surface temperatures are measured at multiple points. Sensors on the lunar module and instruments left on the ground provide continuous data, confirming expected conditions. Every reading matches the predictions derived from prior orbital measurements and physical principles. The environment is stable and predictable, allowing the crew to plan extravehicular activity based on real data. You reflect on how each stage of descent and landing is documented numerically. Speed, altitude, acceleration, fuel consumption, and orientation are all recorded and transmitted. Ground-based radar and optical instruments provide independent confirmation of the lander's path. Every measurement is quantifiable, verifiable, and repeatable. The landing is not a matter of speculation. It is an orchestrated application of physics, tested systems, and continuous measurement. As you rest in the understanding of this precise descent, you recognize that the module's contact with the lunar surface represents the culmination of extensive planning and measurement. Every factor, from thrust control to dust displacement, is grounded in documented physics. The spacecraft is at rest, ready to allow humans to move across the surface, conduct experiments, and collect samples. The moment of landing is a fully measurable event, recorded from multiple angles and confirmed by telemetry. You settle with the awareness that each second of descent was carefully calculated and verified. The engines, guidance systems, and environmental sensors functioned exactly as physics predicted. The moon is beneath the module, stable and observable. And as you watch the lander rest quietly, you feel a gentle anticipation for the first steps on this other world, where low gravity, lunar dust, and measured motion will soon be experienced in the tangible, predictable environment confirmed by observation and instrumentation. You imagine stepping from the lunar module onto the surface of the moon. The lower gravity, roughly 1/6 that of Earth, means each movement takes less force, yet momentum is preserved differently. When an astronaut pushes off the surface, the resulting trajectory is longer, and braking requires careful adjustment. Engineers measured this during training in lunar simulators and during the missions themselves, confirming that motion is predictable under these gravitational conditions. Each step can be calculated in terms of applied force, mass, and acceleration, just as Newton's laws describe. The lunar regolith itself behaves differently from soil on Earth. It is fine, powdery in some areas, and compacted into small rocks in others. Footprints create depressions whose depth corresponds directly to applied force and the particle cohesion of the soil. Measurements taken during the missions show that the regolith compresses predictably under weight and retains its shape, providing evidence of the mechanical properties of lunar dust. These observations are verified by photographs, telemetry, and subsequent analysis of returned samples. Walking, or more accurately bounding, is constrained by the spacesuits. Each suit has joints, layers of material, and life support equipment that slightly resist motion. Engineers measured the torque required to move limbs, and astronauts adapted their gait to maintain stability and efficiency. The effects are predictable. Slower, deliberate movements reduce the risk of tipping, while careful pushes off the surface produce arcs that can be calculated using mass, gravity, and applied force. Every action follows the principles of classical mechanics. Shadows on the moon are sharp and well-defined because there is no atmosphere to scatter sunlight. Measurements of illumination show that light intensity varies with angle and reflectivity of the surface. Brightness contrasts are recorded in mission photographs and are consistent with calculations based on solar incidence and lunar albedo. No assumption is needed. The behavior of light is confirmed by observation and documented across multiple locations visited during the Apollo missions. The astronauts carried tools and instruments while walking. The mass of these objects affects the forces required to move and balance, which engineers accounted for in pre-flight training. Every movement of tools, cameras, or sample containers obeys the same physics as free motion on the surface. The resulting motions and trajectories were observed, measured, and recorded, providing precise data on how humans could operate in low-gravity conditions. You notice how surface irregularities influence movement. Small rocks, craters, and slopes alter trajectories and require micro-adjustments in walking or bounding. The astronauts learn to measure and respond to these variations in real time, adjusting foot placement and force application. Each adjustment is grounded in measurable physical properties: the slope, the regolith cohesion, and the astronaut's mass. Video analysis confirms that all maneuvers were deliberate, predictable, and consistent with known mechanics. Lunar dust responds to pressure and motion in measurable ways. When a foot or tool makes contact, particles displace along predictable vectors, unaffected by wind or air. These patterns were recorded in photographs and video, showing arcs and dispersions that match calculations based on gravity and particle physics. The dust's interaction with the boots and tools is consistent with the properties determined from returned samples, confirming the behavior of fine-grained lunar soil in a vacuum. Handholds and sampling techniques are guided by measurement. Astronauts applied forces calculated to avoid tipping or destabilizing their center of mass. The placement of tools and samples follows principles of leverage and torque, ensuring that movement is controlled. Sensors in the suits, combined with video analysis, show that each motion obeys predictable laws, providing a clear map of how humans interact physically with the lunar environment. Reflections and lighting are measured carefully. Cameras record brightness and shadow with calibrated sensors, confirming that illumination matches predictions based on sun angle and surface reflectivity. The lack of atmosphere ensures that light travels in straight lines, producing sharp shadows and high-contrast images. Observations are consistent across multiple missions and locations, and the data allow scientists to understand how light behaves on airless bodies. Astronauts' footprints serve as long-term markers of physical interaction with the surface. Measurements of depth, width, and dispersion indicate applied forces and motion paths. Over time, these depressions remain virtually unchanged due to the absence of wind and water. Analysis of photographs and returned samples confirms the mechanical properties of the regolith and the accuracy of predictions made using terrestrial analogs. The prints provide evidence of human activity and a record of predictable physical interactions. Movement in low gravity also affects inertia. Once an astronaut starts moving, stopping requires calculated application of counterforce. Video frames demonstrate how astronauts slowed themselves before reaching obstacles or inclined terrain. Every adjustment obeys classical laws, confirmed by analysis of acceleration and mass. This predictability allows safe, repeatable locomotion across the surface, with each motion verified through observation and measurement. You observe the interaction between lunar soil and equipment. Tools, sample containers, and cameras leave impressions or create particle displacement patterns that correspond precisely to applied force. Engineers can calculate these effects in advance, and measurements confirm the predictions. Even the smallest movements, when recorded, produce data that can be quantified and reproduced in simulations. The accuracy of these measurements reinforces the reliability of the recorded human activity. Resting periods on the surface are also controlled. Astronauts sit or kneel in ways that distribute mass safely across the terrain. Pressure sensors in suits and photographs of resting positions confirm that weight is managed predictably. The moon's reduced gravity, combined with suit design, allows stable support without unanticipated slipping or collapse. Every interaction with the surface is consistent with verified measurements of mass, force, and gravity. Sampling procedures rely on precise measurement. Instruments record depth, angle, and pressure applied to soil and rocks. These readings are confirmed by photographic documentation and subsequent analysis of returned samples. Each interaction is quantifiable, and the physical behavior of soil and rocks matches predictions made before the mission. The actions are deliberate, consistent, and measurable, forming a complete record of human activity in a low-gravity, airless environment. As you reflect on the entire experience, you recognize that the astronauts' movements, the soil response, and the interplay of light and shadow all follow precise, measurable physical laws. Every footprint, every bounded step, every tool placement is evidence of predictable motion under lunar conditions. Observations are confirmed by video, photography, telemetry, and sample analysis. No assumption is required. The behavior of humans and environment alike can be measured and quantified. You end quietly appreciating the subtlety and precision of human motion on another world. Standing on the surface of the moon is not only a visual experience but a demonstration of predictable physics in action. The interplay of mass, force, gravity, and friction, all measured, documented, and verified. Each movement aligns with scientific expectation, leaving a calm understanding of how humans operate when removed from Earth's familiar pull. The environment is stable, the laws of motion reliable, and the next task, collecting samples and recording measurements, awaits, guided entirely by verifiable science. You begin by observing the carefully packaged rocks and regolith the astronauts collected. Each sample is documented with location, orientation, and depth, ensuring that later analysis can be correlated with its exact lunar environment. The collection procedures followed precise measurements. The astronauts used tongs, scoops, and containers calibrated to prevent contamination and preserve mass. Even the smallest particles were recorded, creating a comprehensive dataset of lunar surface materials. The moon rocks themselves reveal measurable properties that distinguish them from terrestrial samples. Mineral content is analyzed using spectroscopy, X-ray diffraction, and chemical assays. Oxygen isotopes, for instance, show ratios distinct from Earth while maintaining similarities that support the giant impact hypothesis of lunar formation. These measurements are reproducible, verifiable, and provide evidence of the moon's origin and differentiation. Every property measured corresponds to established physical and chemical laws. Crystal structures within the rocks display evidence of formation processes. Plagioclase, pyroxene, and olivine minerals are found in specific arrangements, reflecting cooling rates and thermal history. Geologists confirmed these structures through electron microscopy and X-ray analysis. Each sample's crystallography is documented, measured, and reproducible, allowing scientists to compare lunar formation to terrestrial geology. The findings align with the physical principles of mineral formation under known conditions. Seismic instruments left on the surface provide ongoing data. When meteorites strike or internal quakes occur, vibrations are transmitted through the moon and recorded in precise digital units. The measurements allow determination of the moon's internal structure, including crust thickness and core properties. These readings are not estimates. They are continuous, recorded data, verified against multiple instruments and timestamps. Analysis confirms the moon has a differentiated structure similar in some ways to Earth but scaled according to size and composition. Regolith samples provide insight into surface processes. Grain size, composition, and angularity are measured using sieves and microscopes. The fine dust is found to be highly abrasive, evidence of billions of years of micrometeorite impacts. Each grain's shape, density, and composition is recorded, providing a quantifiable map of lunar surface conditions. These measurements confirm observations made by orbital sensors and previous unmanned missions. You notice how retroreflectors left on the surface continue to return laser pulses from Earth. By timing the round-trip travel of light, scientists measure the distance to the moon with centimeter-level precision. These measurements are exact, based on the known speed of light and geometrical calculations. They provide ongoing verification of lunar distance, orbital dynamics, and even subtle effects like tidal acceleration. Each laser pulse produces data that can be repeated and verified independently by multiple observatories. All samples undergo chemical analysis in controlled laboratories. Spectrometers, mass analyzers, and electron microscopes measure elemental and isotopic composition. These readings are precise, providing quantitative evidence rather than qualitative interpretation. For example, the ratios of isotopes such as oxygen 16, oxygen 17, and oxygen 18 are compared to Earth standards to confirm the moon's shared history and differentiation process. Each measurement is reproducible and consistent across independent laboratories. Geophysical measurements complement the material samples. Accelerometers on deployed instruments detect microvibrations caused by meteoroid impacts, thermal expansion, and internal lunar movement. The data are time-stamped and transmitted back to Earth, allowing scientists to build a continuous, accurate model of lunar geophysics. Every reading is measurable, verifiable, and aligned with physical laws governing waves and vibration in solid materials. The process of bringing materials back to Earth is meticulously measured. Containment, transport, and handling are monitored for contamination, temperature, and pressure. Scientists track each sample's mass, location, and storage conditions. Measurements confirm that the material returned is identical to what was collected on the moon, preserving the integrity of the dataset. Laboratory analysis begins immediately, following procedures validated through decades of prior research in planetary science. Returned samples provide evidence of lunar volcanic activity. Basaltic rocks reveal cooling histories measured through radiometric dating. Decay of isotopes like uranium-238 and potassium-40 allows scientists to calculate formation ages, providing a timeline of lunar geological activity. These methods are exact and repeatable, forming the backbone of our understanding of the moon's evolutionary history. Each calculation is grounded in laboratory measurements and fundamental decay laws. The moon rocks also reveal exposure to cosmic radiation. Measured quantities of isotopes such as helium-3 and neon-21 indicate bombardment by solar particles over millions of years. These readings match predictions from models of solar wind flux and cosmic ray interactions, confirming the long-term exposure history of the lunar surface. The isotopic data provide measurable insight into the radiation environment beyond Earth's atmosphere. Regolith compaction and layering are studied using returned cores. Depth, particle size distribution, and density are measured, showing how micrometeorite impacts and thermal cycling shape the surface. These physical measurements are consistent with orbital imagery and lunar surface photographs. The physical structure of the lunar soil is mapped and quantified, allowing engineers to design future landers and habitats based on accurate, measured properties. You see that the retroreflectors also serve as long-term markers of human activity, providing exact reference points for distance measurements. Scientists use laser ranging to track the moon's orbit, measure tidal acceleration, and confirm the stability of the lunar surface. Each pulse provides reproducible data, allowing decades of continuous study. These results are precise, independent, and scientifically validated, demonstrating the enduring impact of instruments left behind. The combination of rocks, soil, and geophysical instruments forms a complete dataset. Chemical composition, isotopic ratios, crystal structures, and physical measurements are all documented and cataloged. Analysis confirms the moon's volcanic history, impact processes, and internal structure. Every observation is rooted in measured evidence and reproducible testing, leaving no room for assumption. Each dataset can be cross-referenced with orbital measurements, photographs, and seismic readings. In laboratories, isotopic ratios of returned samples continue to inform models of planetary formation. Comparing Earth and Moon samples provides measurable evidence supporting the giant impact hypothesis. Variations in trace elements and mineral composition confirm that the Moon and Earth share a common origin while exhibiting unique characteristics. Each piece of data is measurable, verified, and aligns with physical and chemical laws. The astronauts also documented their sampling procedures extensively. Video recordings and photographs show how each sample was extracted, packaged, and stored. Mass measurements of each sample are recorded before leaving the Moon and upon arrival on Earth. These measurements confirm that the material remained unchanged in transit, preserving the integrity of physical and chemical analyses. Every step is monitored and verified using precise instrumentation. Return data confirm not only the Moon's composition but also its suitability for future study. Engineers and scientists use measured properties of regolith and rocks to design tools, habitats, and instruments for subsequent missions. Thermal conductivity, density, particle size, and compaction data are all measured values that inform engineering calculations. These measurements provide a scientific basis for future exploration, ensuring that predictions match real-world conditions. As you rest in the understanding of what the astronauts brought back, you recognize the depth of measurable knowledge obtained. Rocks, soil, seismic data, and retroreflectors provide a complete and verifiable record of the lunar environment. Every sample and instrument is accounted for, analyzed, and documented, forming a foundation for ongoing scientific study. Observations are consistent, repeatable, and grounded in measurable physical principles. You end with a quiet appreciation for the tangible evidence of human exploration. The Moon's surface, sampled and studied, provides precise information about its origin, structure, and ongoing interactions with the solar system. Every reading, measurement, and sample collected reinforces a sense of scientific certainty. And as the knowledge returns to Earth, it gently prepares you to follow the astronauts on the journey back home, guided entirely by measured physics and real-time telemetry. You begin by observing the lunar module's ascent from the Moon's surface. Engines ignite to lift the ascent stage off the regolith, and thrust is carefully controlled to achieve the planned velocity. Measurements of acceleration, fuel consumption, and trajectory are continuously monitored by onboard instruments. The craft follows a path calculated to rendezvous precisely with the command module, using orbital mechanics confirmed through prior simulations and mission data. Every movement is predictable, grounded in Newton's laws and verified by telemetry. The ascent is carefully timed. Lunar gravity, although lower than Earth's, requires precise calculations to reach the correct orbit. Engineers plan the burn so that velocity and altitude intersect the command module's trajectory. The spacecraft's mass decreases as fuel is consumed, and instruments track this change in real time. The guidance system makes minor adjustments, measured and verified, ensuring that the module remains on the correct path. Telemetry confirms each stage of acceleration and course correction, providing independent confirmation from Earth-based tracking. Docking with the command module involves precise maneuvers. Relative velocities are measured using radar and optical sensors. Thrusters provide small, controlled impulses to align the two spacecraft. The process is monitored both by the astronauts and by mission control, with telemetry confirming that approach, alignment, and capture occur exactly as predicted. The physics of motion, reaction forces, and angular momentum are applied consistently, allowing a smooth connection between the two vehicles. Once docked, the crew transfers equipment, samples, and themselves back into the command module. Mass balance and center of gravity are measured to maintain stability for the return trip. Fuel usage and propulsion parameters are recalculated to account for the combined mass. Sensors record every variable, providing real-time verification that systems remain within operational limits. All calculations are based on documented measurements and established physics. The trajectory toward Earth is carefully controlled. Mid-course corrections are executed using thrusters, guided by precise velocity and position measurements. Each correction is small but measurable, with adjustments calculated using orbital mechanics. Ground stations track the spacecraft using radar and radio telemetry, providing independent confirmation of the path and speed. Every movement is consistent with Newtonian mechanics, and all data are verifiable. Re-entry begins as the command module approaches Earth. The spacecraft enters the atmosphere at a precise angle, calculated to maximize deceleration while minimizing thermal stress. Heat shields are engineered to absorb and radiate energy, preventing temperatures from exceeding material limits. Sensors on the module record temperature, pressure, and structural stress throughout re-entry. These measurements confirm that the design performs exactly as intended. Shock layers form as air is compressed in front of the spacecraft. The resulting plasma produces heat that the heat shield absorbs and radiates. Measurements from onboard instruments show the distribution of temperature and pressure over the module's surface. Every reading aligns with calculations made during the mission's engineering phase. Observations confirm that re-entry is a controlled physical process, governed entirely by fluid dynamics and thermodynamics. Parachute deployment is carefully measured. Sensors detect deceleration and altitude, triggering drogue and main parachutes at predetermined points. The forces exerted by the parachutes are measured in real time, confirming that the module slows safely for splashdown. Calculations made before the mission match the measured descent rate and final velocity. Each stage is validated by telemetry, ensuring that the landing is within safe parameters. Splashdown occurs in the predetermined recovery zone. Water depth, wave height, and impact forces are measured, confirming that the module settles safely. Buoyancy is predictable based on mass and volume, and recovery procedures rely on these measurements. The crew's safety is verified through continuous monitoring of instruments and position. Every aspect of the return aligns with the physics calculated before departure. Earth-based tracking stations provide continuous verification throughout the mission. Radar, optical instruments, and radio telemetry confirm speed, position, and trajectory at every point. These independent measurements cross-check onboard sensors, ensuring consistency and reliability. Observed data match predictions based on celestial mechanics and spacecraft design parameters. The journey home is precisely documented, leaving no ambiguity in the spacecraft's path or behavior. Once aboard the recovery vessel, samples and equipment are removed and cataloged. Mass, identity, and condition of each item are measured to confirm integrity after re-entry and splashdown. This ensures that all scientific material is preserved exactly as collected on the Moon. Temperature, humidity, and mechanical stress during retrieval are monitored to maintain sample quality. Every parameter is quantifiable and verified, providing confidence in the scientific return. The astronauts themselves are monitored carefully for physiological responses. Heart rate, respiration, and other vital signs are measured continuously. The data provide information on human adaptation to microgravity, acceleration, and re-entry forces. Measurements confirm that the crew remains within safe limits throughout the return process. No assumption is necessary. Every reading is objective and reproducible. Mission logs document each maneuver, reading, and observation. The ascent, docking, trans-Earth injection, and re-entry are all recorded with precise timestamps. Every measurement is backed by sensors and ground-based verification, creating a comprehensive dataset of the entire mission. Analysis of these logs confirms that the physics of each stage, acceleration, orbit insertion, thermal protection, and splashdown, is entirely consistent with established scientific principles. The return trip is also a demonstration of human and engineering coordination. Ground control and onboard systems operate in a closed feedback loop, responding to measured values of velocity, acceleration, and position. The combination of automatic systems and human observation provides a redundant, measurable verification of every maneuver. Each stage is predictable, consistent, and supported by independent tracking. As you rest in the understanding of this return, you recognize that every second of the journey is governed by measurable physical laws. From lunar ascent to splashdown, each motion, force, and observation is recorded and verified. Telemetry, radar, sensors, and video all provide data confirming that the mission follows predictable paths based on physics and engineering. The spacecraft behaves precisely as calculations and measurements predicted. You end quietly appreciating the precision and reliability of the mission. The astronauts have returned safely, the scientific samples remain intact, and every maneuver is documented and measurable. The data gathered during the trip home reinforces the trust in physics, engineering, and observation. The Earth receives the returning spacecraft with predictable forces and verifiable outcomes, leaving a calm awareness of the tangible, measured success of human exploration. You begin by observing the ongoing presence of equipment left on the Moon. Laser retroreflectors placed by the Apollo astronauts continue to reflect laser pulses sent from Earth. Scientists measure the round-trip travel time of these pulses, calculating the distance to the Moon with centimeter-level precision. These measurements are exact, repeatable, and independent of any human observation. Multiple observatories worldwide confirm that the retroreflectors are positioned precisely where mission records indicate. The reflections match the expected geometry, providing tangible proof of the lunar landing locations. Radio transmissions provide another layer of verification. During the missions, signals from the lunar module, command module, and astronauts were received by multiple Earth stations, including tracking networks outside the United States. Frequencies, signal strength, and Doppler shifts match the predicted positions and velocities of spacecraft in lunar orbit and on the surface. Independent monitoring stations, such as those in Australia and Spain, recorded the same signals, confirming the physical presence of humans on the Moon. These signals are measurable, recorded, and verifiable, leaving no ambiguity about the missions. Orbital tracking of the spacecraft also confirms the landings. Radar measurements of both the command and lunar modules, along with optical observations from Earth and other satellites, match the planned trajectories exactly. The paths correspond to calculated orbital mechanics with velocity, acceleration, and timing consistent with predictions. Observations are independent, reproducible, and documented in mission records. Every adjustment, course correction, and orbit insertion was observable and measurable, confirming that the spacecraft followed the intended paths to and from the Moon. The lunar samples provide additional, independent evidence. Rocks and soil brought back have isotopic ratios, mineral composition, and crystal structures that are unique to the Moon. Laboratory analysis shows that oxygen isotopes, elemental abundances, and trace minerals are consistent with lunar origin and distinct from terrestrial material. Seismic data collected by instruments left behind align with the measured properties of the lunar interior. Every analysis is based on quantitative, repeatable measurements that provide strong physical evidence of human activity on the Moon. Multiple national space agencies have verified the missions through independent observations. Orbiters from Japan, China, India, and the United States have imaged Apollo landing sites, showing lunar modules, rover tracks, and astronaut paths. High-resolution photographs reveal the precise locations of equipment and disturbances in the regolith that correspond to mission documentation. Measurements of dimensions, angles, and reflectivity align exactly with records from 1969 through 1972. This independent verification provides additional confidence in the authenticity of the landings. The engineering aspects also support verification. The complexity of launching a Saturn V rocket, navigating to lunar orbit, landing safely, and returning would require enormous resources and precise physics. Each stage has measurable outcomes: thrust, acceleration, trajectory, and timing. Instruments, telemetry, and observational data confirm that these stages occurred as planned. Replicating these events on Earth, without leaving measurable traces or samples on the Moon, would defy physical feasibility. Analysis of lunar surface conditions further corroborates the landings. Dust behavior, footprint retention, and lighting in photographs match the properties of a vacuum environment. No atmospheric scattering occurs, shadows are sharp, and dust arcs are consistent with measured gravity and engine thrust. The scientific community can replicate these effects in controlled environments, confirming that the photographs and videos could only result from activity in a lunar environment. Measurements of regolith properties and soil mechanics confirm the authenticity of observed interactions. Laser ranging experiments continue to produce verifiable results decades after the missions. Every pulse of light that returns provides a precise measurement of the Moon's distance and orbit. These readings align with gravitational models and orbital predictions. Independent observatories reproduce the measurements, confirming the continued presence of Apollo retroreflectors. The ongoing functionality of these instruments offers physical evidence that astronauts deployed them exactly as documented. The signals recorded during extravehicular activity also provide verification. Communications logs, time-stamped and synchronized with Earth-based tracking, match the sequence of movements, sample collection, and observations documented in transcripts. Every audio cue and recorded transmission can be correlated with photographs, video frames, and surface measurements. The synchronization of multiple datasets provides a cross-confirmed, measurable record of activity on the lunar surface. Astronaut footprints provide additional quantifiable evidence. Depth, spacing, and orientation are consistent with human movement under lunar gravity and suit constraints. Analysis of high-resolution images from lunar orbiters confirms the precise locations of these tracks. Every footprint aligns with video and photographic evidence, producing a measurable map of astronaut activity. The physical imprint of human presence remains unchanged over decades, preserved by the Moon's stable environment. Meteorological and astronomical considerations also support verification. Timing of landings corresponds with precise lunar phases and illumination angles, as calculated before the missions. Photographs show shadows, light intensity, and surface reflectivity consistent with these calculations. Independent observations from Earth telescopes confirm that conditions matched predictions at the time of landing. These measurements are consistent, repeatable, and documented. All lunar samples have been analyzed in multiple laboratories worldwide. Oxygen isotopes, rock composition, and mineral structures are consistent across independent studies, leaving no doubt about their origin. These measurements follow established physical and chemical laws. Variability between samples aligns with different lunar locations, confirming that material was collected from multiple sites rather than manufactured or transported artificially. Every finding is measurable and scientifically validated. You also consider the instruments left on the surface. Seismometers, retroreflectors, and other sensors continue to transmit data or provide measurable effects that align with documented installation procedures. The orientation, location, and condition of these devices are consistent with mission logs. Observations are reproducible and measurable, providing independent verification of human activity on the Moon. Every device confirms physical presence and interaction. Taken together, laser measurements, orbital tracking, radio signals, photographs, and return samples form a cohesive, verifiable dataset. Each line of evidence is grounded in measurable physical phenomena. Independent replication by multiple agencies and laboratories strengthens confidence in the results. No plausible physical explanation exists for producing this body of evidence without actual lunar landings. Every claim aligns with observation, measurement, and established science. As you reflect on the combination of data, you recognize the breadth and precision of verification. Instruments, samples, and observations converge to confirm the presence of humans on the moon. Physics, chemistry, optics, and geophysics all provide measurable, reproducible support. Independent tracking, laser ranging, and laboratory analysis produce results that align exactly with predictions and mission documentation. The moon is mapped, sampled, and instrumented with a level of precision that is observable from Earth and verified worldwide. You end quietly with a sense of confidence grounded in data. Human activity on the lunar surface is verifiable through multiple, independent, measurable methods. The landings are not conjecture. They are confirmed by physics, chemistry, orbital mechanics, and observation. Every record, instrument, and sample provides evidence that can be measured, repeated, and independently validated. The moon bears the marks of human exploration, leaving a calm and factual understanding of what truly occurred. You begin by observing shadows in photographs taken on the lunar surface. Some viewers note that shadows appear to diverge or fall at unusual angles. Measurements of light sources, solar incidence angles, and lunar surface topography clarify this effect. The moon's surface is uneven, with craters, rocks, and slopes, causing shadows to intersect in ways that can appear unusual from a two-dimensional perspective. Calculations of light paths, based on the sun's position and measured surface elevations, confirm that the shadows are fully consistent with a single, distant light source in a vacuum. The behavior of the American flag is another commonly discussed topic. On Earth, flags hang or wave in response to air currents, but the moon has no atmosphere. Observations from mission recordings show that the flag's movement occurred when astronauts handled it. Measured forces from inserting the pole and adjusting the fabric caused vibrations that persisted briefly due to the flag's inertia and the low lunar gravity. Physics predicts that without air resistance, motion continues longer, which matches exactly what is observed in video footage. No wind or artificial movement is necessary to explain the flag's position. The absence of stars in photographs is also frequently questioned. Cameras used by astronauts had fast shutter speeds and lenses set for daylight exposure to prevent overexposure of the bright lunar surface. Measurements of light intensity show that stars, being far dimmer than the sunlit surface, do not appear under these settings. Optical physics explains this completely. Sensors capture light according to exposure and aperture, and stars are too faint relative to the illuminated moon. Observations from multiple Apollo missions confirm that adjusting exposure settings can capture stars, but standard mission photography prioritizes surface detail. Radiation exposure is another topic that can be measured. The Apollo spacecraft passed through the Van Allen belts, regions of charged particles trapped by Earth's magnetic field. Instruments recorded the levels of radiation encountered. Measurements indicate that exposure was within safe limits for the short passage, with shielding and trajectory carefully calculated to minimize dose. Astronaut health monitoring confirms that radiation levels remained below thresholds known to cause acute harm. The physical data correspond precisely with predicted models of particle flux and shielding effectiveness. Photographs and video provide further evidence when examined with measurable properties. Lighting, contrast, and perspective are all consistent with known lunar conditions. Cameras were calibrated, and the effects of the vacuum and low gravity on dust, footprints, and tool handling are all predictable. The orientation and scale of objects match measurements of distances and angles taken from lunar surface coordinates. Independent scientists have measured these factors, confirming that images align perfectly with documented mission parameters. The lunar surface's reaction to foot traffic also addresses misconceptions. Critics sometimes suggest that footprints are inconsistent or suspicious. Measurements of regolith density, compressibility, and cohesion show that the moon's soil responds predictably to weight. Footprint depth correlates with applied force and boot area. Experimental simulations on Earth with lunar analog soil reproduce similar depressions. High-resolution photographs taken by orbiters confirm that astronaut tracks match these measured behaviors, providing independent verification of physical interactions. Dust displacement during landing has also been questioned. Observations from mission footage and photographs show arcs of regolith moving outward from the descent engine. Measured thrust, engine height, and lunar gravity predict the trajectory of displaced particles. Particle behavior in a vacuum is consistent with Newtonian mechanics. Without air resistance, dust follows ballistic arcs determined by the force applied and gravitational acceleration. Independent calculations confirm that observed dust behavior aligns with expectations based on the engine's known performance. The lunar module's appearance in photographs is measured and consistent with mission documentation. Relative sizes, angles, and positions match the module's known dimensions. Telemetry provides recorded orientation and coordinates at each location, which can be cross-checked with images. Shadows, lighting, and perspective all correspond to verified solar angles and surface topography. Analysis of these factors provides measurable evidence that the module was on the lunar surface at the reported locations. Reflections and surface brightness also follow predictable behavior. Albedo, or reflectivity, of lunar soil is measured at approximately 0.12, meaning it reflects 12% of incident sunlight. Photographic and video exposure match these measurements. Brightness gradients and diffuse reflection can be modeled accurately using these physical properties, and the observed images are consistent with such calculations. Independent measurements from lunar orbiters and Apollo instruments confirm the accuracy of these observations. Audio recordings further support authenticity. The voices of astronauts are transmitted through radio signals from the lunar module and command module, recorded on multiple Earth stations. Signal strength, Doppler shifts, and timing correspond precisely to the positions and movements of the spacecraft as measured independently. Engineers verified that the delay and quality of transmission matched expected propagation times for signals traveling over 380,000 kilometers. Every variable can be calculated and measured to confirm physical consistency. Lunar dust adherence to suits and tools also matches measured properties. Microscopic analysis of return samples shows fine, angular grains that cling electrostatically. Photographs and videos of the astronauts demonstrate predictable dust behavior, including accumulation in folds of fabric and on gloves. Laboratory simulations using lunar analogs reproduce the same clinging effects under low gravity and vacuum conditions. Observed phenomena are thus entirely consistent with measured physical and electrostatic properties. Surface temperature measurements confirm claims about the environment. Daytime temperatures near the equator reach approximately 120 degrees Celsius, while nighttime drops to around -170 degrees Celsius. Instruments left on the surface and temperature readings from return samples verify these values. Photographic evidence, shadows, and astronaut actions all correspond to these measured temperatures. Every observation aligns with scientific predictions based on the moon's lack of atmosphere and thermal conductivity. Even the mechanics of moving equipment are consistent with measured forces. Cameras, sample containers, and tools behave predictably under 1/6 Earth gravity. Video analysis confirms the acceleration, momentum, and braking actions of astronauts moving these objects. Every interaction is reproducible in simulation, confirming that human activity in low gravity and vacuum produces the observed results. Physics accurately predicts every motion. Taken together, shadows, flags, stars, radiation, photography, dust behavior, and surface interactions are all resolved through measurable science. Each point of confusion can be addressed using documented data, controlled experiments, and independent verification. Observations from multiple Apollo missions, combined with subsequent orbiters and laboratories, provide a coherent, fully measured explanation for each commonly cited misconception. You end with a quiet sense of clarity. Understanding the physics, measurements, and verified observations dissolves apparent contradictions and leaves only consistent, evidence-based conclusions. The moon landings are fully supported by measurable phenomena, and every detail can be explained using predictable, reproducible science. The calm certainty of physical verification provides reassurance that confusion can always be resolved through observation, measurement, and logical analysis. You begin by observing the ripple effects of the Apollo program on science and technology. The materials developed for spacecraft and spacesuits introduced new alloys, insulation, and composite structures. Engineers tested tensile strength, thermal resistance, and flexibility under measured conditions. These innovations were documented and reproducible, forming the foundation for numerous industrial and scientific applications. Every improvement is traceable to laboratory testing and mission requirements, showing a direct, evidence-based benefit. Computing also advanced through the Apollo missions. The onboard guidance computer, though primitive by modern standards, operated using measurable electronic principles: voltage, current, binary logic, and memory storage. Engineers validated every instruction and timing sequence through rigorous testing and simulations. The lessons learned influenced computer miniaturization, reliability, and real-time processing, measurable advances that persist in modern technology. Every calculation and data point was subject to verification, demonstrating the practical application of physics and engineering. Navigation improvements emerged as another measurable outcome. The Apollo program relied on precise inertial guidance and star-based navigation systems. Accelerometers and gyroscopes provided continuous data to track velocity and position, with telemetry confirming accuracy. These instruments allowed engineers to calculate trajectories with predictable precision. Independent verification from Earth-based tracking confirmed that the spacecraft followed the predicted paths. The accuracy and reproducibility of these systems illustrate a tangible, measurable benefit to both spaceflight and terrestrial navigation technologies. Geology benefited directly from lunar exploration. Return samples and seismic instruments provided precise data about the moon's structure, composition, and formation history. Measurements of isotopic ratios, mineral content, and rock textures informed models of planetary differentiation and volcanism. Data from the moon remain in databases used to test hypotheses about Earth and other planetary bodies. Every dataset is reproducible, verified, and measurable, contributing directly to our understanding of planetary formation processes. The program also influenced physics education and scientific methodology. Students and researchers study Apollo mission data, calculating trajectories, analyzing seismic readings, and modeling thermal loads. Measurable outcomes, such as sample composition or orbital mechanics, provide clear examples of applied physics and engineering. Every experiment and dataset is fully documented and replicable, allowing ongoing learning from real-world, verified evidence. This creates a lasting, educational foundation grounded in observation. Instrumentation improvements were another measurable result. Temperature sensors, pressure gauges, accelerometers, and cameras developed for the Moon program demonstrated unprecedented precision. These instruments were calibrated against standards and verified in test environments. Engineers documented every measurement, ensuring reliability. The precision and repeatability of these tools have had long-lasting impacts on fields ranging from meteorology to structural engineering. Every instrument reflects careful, evidence-based design. Medical science also advanced measurably. Monitoring astronaut physiology during launch, microgravity exposure, and re-entry provided quantitative data on cardiovascular function, bone density, and muscle atrophy. Measurements of heart rate, blood pressure, and metabolic changes guided the development of countermeasures, including exercise protocols and dietary adjustments. These insights are documented, reproducible, and applied to both space medicine and Earth-based healthcare. Every physiological measurement contributes to understanding human adaptation to extreme environments. Lunar mapping and orbital science continue to provide verifiable knowledge. Remote sensing data, including spectral imaging and laser altimetry, map the moon's surface with measurable precision. These measurements confirm and extend what astronauts observed on site. Data analysis allows accurate modeling of topography, mineral distribution, and gravitational anomalies. Each dataset is reproducible and independently verified, supporting ongoing research in planetary science. Observations provide measurable, evidence-based insights into lunar geology and structure. The Apollo program also catalyzed environmental and systems engineering studies. Life support systems, thermal control, and energy management were tested under extreme, measurable conditions. Engineers recorded temperature gradients, humidity, and oxygen levels, analyzing system performance. These metrics informed the design of sustainable habitats, both in space and in terrestrial analogs. Every parameter was quantified and verified, demonstrating how careful measurement drives effective design and innovation. Cultural significance, though not measurable in the same way, is supported by verifiable outcomes. The development of international tracking networks, educational programs, and documented achievements provides evidence of societal impact. Public and professional engagement, measurable through participation rates, publications, and archival records, reflects the program's enduring influence. Data on global observation and scientific collaboration illustrate a tangible result of the missions beyond purely technical achievements. Economic and industrial impacts are also grounded in measurable data. Manufacturing techniques, materials testing, and precision engineering developed for the Moon program led to quantifiable improvements in productivity and product reliability. Patents, production records, and efficiency metrics show measurable economic outcomes. Each technological advancement can be traced directly to the requirements and testing associated with lunar exploration. These results are recorded and verifiable, demonstrating practical benefits to society. The Moon landings also provided a benchmark for international verification of scientific claims. Laser retroreflectors, radio telemetry, and orbital tracking offered independent, measurable proof of human activity on the Moon. This framework of cross-verified evidence continues to inform how scientific exploration is documented and confirmed. Every measurement reinforces the reliability of mission data and establishes standards for future exploration. The ongoing availability of these instruments provides continuous verification of the lunar environment. You observe that the data returned from Apollo missions continues to inform new research. Modern studies of planetary formation, lunar volcanism, and space radiation rely on measurements that were collected decades ago. Each dataset is recorded, reproducible, and cross-verified by contemporary instruments. The scientific value persists because the observations were precise, measurable, and carefully documented. Analysis can be repeated, confirming previous conclusions and supporting new hypotheses with real evidence. Engineering knowledge from Apollo missions informs current and future space exploration. Rockets, guidance systems, heat shields, and life support designs are all based on measured performance and observed outcomes. Modern spacecraft inherit proven principles validated by decades of telemetry and experiments. Each aspect, from fuel consumption to structural stress, is calculated and verified against historical data, creating a continuum of measured knowledge. This ensures predictable, safe outcomes for ongoing exploration. The Moon landings also inspire practical applications on Earth. Materials, sensors, and computing technologies developed for space missions have measurable applications in industry, medicine, and environmental monitoring. Performance metrics, reliability testing, and precision measurements provide clear evidence of the benefits. Every adaptation can be traced to a documented, measured outcome, showing that exploration produces practical, quantifiable results. The innovations continue to affect everyday technology and scientific research. You end with a calm appreciation for the breadth of human achievement rooted in evidence. Scientific, technological, and engineering progress from the Moon landings is measurable, verifiable, and enduring. Lunar samples, telemetry data, and instrument records continue to provide precise information about space, Earth, and planetary processes. The legacy of measured, documented knowledge leaves a quiet confidence in human ability to explore, observe, and understand the universe. Every calculation, measurement, and verified observation forms a foundation that will support exploration for generations to come. You begin by observing the current landscape of lunar exploration. Multiple space agencies maintain active programs, each with clearly documented objectives and measurable outcomes. NASA's Artemis program aims to return humans to the Moon, beginning with robotic missions to verify landing sites and test life support systems. Instrumentation on these missions collects temperature, radiation, and surface composition data, all recorded and analyzed through established protocols. Every action and measurement follows predictable scientific and engineering principles, verified through independent telemetry. The Lunar Reconnaissance Orbiter (LRO) continues to map the Moon with high-resolution cameras and altimeters. Observations measure topography, illumination angles, and surface reflectivity with centimeter-scale precision. Each dataset is time-stamped, calibrated, and cross-verified with other instruments, providing reliable and reproducible information. These measurements guide landing site selection for future missions, inform geological studies, and allow scientists to monitor lunar environmental changes with precision. The results are fully measurable and support evidence-based planning for human and robotic activity. China's Chang'e program has delivered orbiters, landers, and sample return missions. Every mission is equipped with scientific instruments that measure soil composition, radiation levels, and gravitational anomalies. Returned samples undergo isotopic and mineralogical analysis, producing quantitative data that complement previous Apollo findings. Measurements are performed in multiple laboratories, ensuring reproducibility and independent verification. The data enhance understanding of lunar geology, including areas previously unvisited by humans, providing a solid foundation for ongoing exploration. India's Chandrayaan program contributes similarly measurable outcomes. Instruments detect water ice in permanently shadowed regions, measure elemental abundances, and map mineral distributions using spectrometers. These observations are calibrated against known physical standards and verified through cross-checking with orbiters and ground-based measurements. Every parameter is recorded and reproducible, enabling scientists to build accurate models of the Moon's surface and subsurface composition. The evidence is consistent and directly informs scientific decisions for upcoming missions. Future robotic missions continue to emphasize precise measurement. Lander-based seismometers quantify moonquakes, mapping the internal structure of the Moon. Thermal sensors measure diurnal and seasonal temperature variations, confirming models of heat flow and conductivity. Radiation monitors track particle flux from the Sun and cosmic sources, producing real-time datasets that validate previous predictions. Every reading is traceable to calibrated instruments, providing a reliable basis for both human and robotic operational planning. Sample return remains a priority for future missions. Engineers plan carefully to collect regolith and rock from multiple locations, with measurements of mass, isotopic composition, and contamination risk controlled by standard procedures. The design of collection tools, transport containers, and sample handling follows verified protocols to maintain integrity. Post-return, laboratory analysis provides measurable data on lunar composition, isotopic ratios, and mineralogy. Each measurement is reproducible, adding to the scientific record with quantifiable certainty. Habitat testing on the lunar surface is another area of measurable investigation. Robotic modules and landers carry environmental control systems, sensors, and life support simulators. These instruments record temperature, humidity, pressure, and radiation shielding effectiveness. Every system is calibrated, and measurements are continuously verified. Data collected informs the design of future human habitats, ensuring that engineering principles are applied with precision and repeatability. The evidence supports safe and predictable planning for extended surface operations. Orbital navigation and trajectory control are measured with extreme precision. Modern spacecraft use star trackers, inertial measurement units, and laser altimeters to confirm position and velocity relative to the Moon. Each maneuver is documented with telemetry that can be independently analyzed by mission control and ground-based stations. These verified measurements ensure that every planned landing or orbital adjustment matches predicted outcomes. All orbital actions are quantifiable, based on well-established principles of celestial mechanics and verified data. Scientific instrumentation for lunar study continues to improve. Spectrometers measure elemental abundances, magnetometers track magnetic fields, and gravimeters detect variations in lunar gravity. Data collected is calibrated against standards, cross-verified, and time-stamped to ensure reproducibility. Every reading informs models of lunar composition, internal structure, and geophysical processes. Analysis of this data allows scientists to refine hypotheses about planetary formation and evolution, relying solely on measured evidence. International collaboration also contributes measurable outcomes. Multiple agencies coordinate observations, instrument deployments, and orbital tracking. Data is shared, verified independently, and compared with historical records from Apollo and other missions. Redundant measurements ensure accuracy and provide cross-validation. This cooperative approach produces a global, verifiable dataset, confirming every observation and reinforcing confidence in the findings. Scientific conclusions are drawn only from these verified, measurable sources. Radiation and environmental studies continue to be central. Detectors monitor solar particle events and cosmic rays, providing real-time measurements for risk assessment. Temperature sensors, dust monitors, and surface cameras collect additional environmental data. Each measurement is quantifiable, reproducible, and documented. Observations support engineering design for human missions and robotic systems, ensuring that all operations are based on reliable, evidence-based information. The data forms a continuous record that informs mission planning and safety protocols. Laser ranging experiments, building on Apollo retroreflectors, continue to track the moon's distance and orbital dynamics. Measurements of round-trip light travel times produce precise distance calculations, confirming orbital models. Observatories worldwide perform these measurements independently, reproducing results with high accuracy. This ongoing activity demonstrates that verified, measurable science remains foundational to understanding the moon's motion and interaction with Earth. Every pulse of light reinforces long-term observational consistency. All of these efforts contribute to a calm and systematic understanding of what can be achieved on the moon. Every measurement, observation, and experiment follows established physical principles. Engineers and scientists rely on reproducible data to plan missions, ensuring predictable and safe outcomes. Observations are independent, cross-checked, and continuously validated, creating a body of knowledge that grows steadily with each mission. The scientific approach remains careful, precise, and evidence-based. You also observe that these measurable activities pave the way for future exploration of the solar system. Lunar operations test techniques for resource utilization, habitat construction, and robotic autonomy. Data on regolith properties, radiation shielding, and thermal control informs broader planetary science. Every experiment provides repeatable evidence, allowing extrapolation of results to other celestial bodies while remaining grounded in verified measurements. Scientific exploration continues to expand in scope, guided by reproducible evidence. You end with a gentle curiosity about what will be discovered next. The moon remains a place of ongoing measurement, precise observation, and verifiable experimentation. Instruments continue to collect data, samples provide quantifiable insights, and every mission follows established engineering and physical principles. The calm certainty of measured results leaves a quiet awareness that systematic exploration will continue to reveal new facts about our nearest celestial neighbor, with every observation rooted firmly in reality.